Good morning.
Hello.
All right, just loading the PowerPoint now. All right. All right. So the first thing we're going to be looking at today will be figuring out how if one compound is more acidic than another compound. And the basis of all of this, to begin with, will be that an acid is a compound that produces H plus when we put it in water. A base produces OH minus when we put it in water. And the more acidic compound is the one that produces more H plus. And the last one, this is the one that's hardest to understand, that we need to get a grip on here, is that the compound that produces a more stable anion will produce more H plus. Right, and that's what we'll be focusing on here with these examples that I'm going to show you now. A couple of things that you should be familiar with. We talked about this last time, and that is how to determine a base and an acid, and the base having the OH minus and the acid here having the H plus. And what happens is that when the base reacts with the acid, then what happens is that the base becomes a conjugate acid, and the acid has a conjugate base. So what I'm talking about there is that a base, which is OH minus, to get the conjugate acid, let's see, let's get our drawing program here going. And what we're going to be looking at here are these two definitions that I put down for a conjugate acid and a conjugate base. So to get a conjugate acid, actually let's change that. And this will always be from a base. Simply add H plus to it. And to get a conjugate base, and that will always be from an acid, we remove H plus. It really is that simple. There's no real confusion to that at all. And you can see here, if you ignore the Na, make it Na plus, which is just going to be a spectator ion, effectively what you have is OH minus. What do? We add H plus to it, we get water. With the acid here, we take away the H plus, and we get, again, ignoring the Na as Na plus, this becomes CH3COO minus. All right, so let's look at, I'm going to show you 4 scenarios here where we're going to talk about figuring out which compound is more acidic out of 2 compounds. And the first one here has to do with ammonia, NH3, and methane, CH4. Now, the first thing we always do in this situation is figure out what it looks like once we take away H+, so that we can see what the anions look like. So the NH3 becomes NH2 minus and H+. And that's always the way it's going to be. We talked about this the other day as well when we were talking about how these negatively charged species can form. But we take away the H plus and we get the NH2 minus, we get CH3 minus here. Now balancing the hydrogens is easy. You can see that we have as many hydrogens on each side as we have on the left and the right. And the negative here is because the H comes off as H plus. Now how do I know it's coming off as H plus? This is because we are trying to determine which compound is more acidic, and that's really the key word here. And acids will form H plus in solution. So that's how I know I'm getting H plus. Does anybody have any questions so far? Anybody have any questions so far? Okay. The next thing we want to do is look at the anions and ask ourselves, well, which anion is more stable? The anions, of course, are the NH2 minus and the CH3 minus here. In this instance, the NH2 minus is more stable than CH3 minus because N is more electronegative than C. Now, I know this because of where they are on the periodic table. So let me pull that here. I think I've got a periodic chart somewhere in here. I've certainly got one in the ungraded copy of test 2, so we'll take a look at that. Or maybe I don't. I'll leave that open because I want to get into there anyway at some point. And that being said, I'll probably add a periodic table into. Here we go.
I think there was one on like module 10, maybe.
Yeah, I've got one here. Yeah, found it. All right, there we go. So fluorine is the most electronegative element of all of them. And you can see that whatever's closest to fluorine out of C and N will be more electronegative. And you can see N is closer to F. That makes N more electronegative than C. Now, the point I'm trying to make here is that if an atom is more electronegative, it's going to pull the negative charge in closer to the nucleus. The nucleus is all positive charges, of course, it's all protons. So the nearer you can pull in the negative charge, the more stabilized it becomes. So that means that something more electronegative will always stabilize negative charge better. So the whole premise of what we're talking about here revolves around the fact that NH2 minus is more stable than CH3 minus. Now, if NH2 minus is more stable than CH3 minus, it makes sense that when this thing dissociates, becomes the anion in H+, the more stable the anion is, the more H+ we're also going to get. So you can think of it this way. Think of it like let's say the NH3 produces 2% NH2 minus, while the CH4 produces 1% of CH3 minus. Now, the reason that this would produce more anion is because this NH2 minus is more stable. But if we're getting 2% of the NH2 minus, we're also getting 2% H plus. And here we just get 1% of CH3 minus and only 1% H plus. And the fact we're getting more H plus on the top one means it's going to be more acidic. So that's where this last part comes in, a statement that links anion stability to acidity. So NH2 minus is more stable than CH3 minus, therefore NH3 is more acidic than CH4. Does anybody have any questions? Now, with this next one, I know that a lot of you aren't really familiar with line structures, but the line structures here are really just representing carbons and hydrogens. And here, it's not really that important to understand the line structure in so much as being able to interpret what the picture means, and that's what I'm going to focus on here. So these are what I'm calling inductive effects, and this one relates to distance. So we're comparing these two compounds here, and we're asking ourselves, well, which one of these is going to be more acidic? You can see there's a very clear difference between them. They both have F's attached to them, but in this instance, the F is closer to this carboxylic acid or C double bond O with the OH group, and this F is further away. So what does that mean as far as anion stability goes? The first thing we do is we take these and we split them up in accordance with what we were just talking about. We take the H plus off, and the negative charge will be left on the atom where the H plus resided. In this case, the H is on the O, and we take the H off as H plus, and that leaves a negative charge on the oxygen that remains. So that's what we're doing so far. Does anybody have any questions? Now, I want to point out a couple of things here. First of all, there are also hydrogens on these carbons, and you might be wondering why those couldn't be taken off as H plus. Now, the reason for that is because of what we had said earlier. Oxygen is a lot more electronegative than carbon is, which means that any hydrogen that gets removed is more likely to be removed from the O than it is any of these C's over here. So that's the first thing. The other thing that's different from the previous one is that the negative charge is ending up on the same atom. So the difference in acidity is not explained by a difference in electronegativity as it relates to where the negative charge is located. So here in the first example, it's N negative versus C negative. And over here, it's O negative and O negative. So the difference in acidity can't be explained by a simple difference in electronegativity. So how is the difference in stability explained? Well, we use this bond polarity model here. And bond polarity is a concept that you would have talked about back in Intro to Chem when we were talking about polar covalent bonds. Also, hopefully in Chem 1, you would have seen this concept as well. So let's talk about what these delta pluses and delta minuses mean. So I'm just going to go ahead and draw these out again. Now, if I want to just sort of zoom in on this area here, so I'm just circling those bonds there. What those actually represent are CF bonds. See, if I was to actually go ahead and draw all this in, there would be C's at each of these points. That's the nature of a line structure. We also put hydrogens on them as well, but I'm not going to worry about that. But the whole point is that's a CF bond that we're talking about. Now, when we're looking at a CF bond, the F is more electronegative than the C, so we can assign these charges to each end, partial charges to each end of the CF bond. So the F gets a delta minus and the C gets a delta plus. But delta minus is telling us that the electron density in that bond is closer to the F than it is to the C. Now, the way you can think about that is think of a bond as being two electrons, and those two electrons being closer to the F than they are to the C. And if that's the case, then that means the electron density overall is closer to the F than it is to the C, which leads to us being able to draw this kind of diagram where we've got a delta plus and a delta minus. So you can see I've done that over here as well. And when we're doing this, the delta plus is on that atom, delta minus on this atom here, delta plus on the C, the delta minus on the F in each instance. All right, does anybody have any questions so far? So what we can talk about now is which anion is more stable and why. It turns out that if I was to label these, I'll label this one AH and this one A minus, makes it a bit easier for me to talk about them. I can say A minus is more stable because the delta plus is closer to the O negative. And what that does is it leads to greater stabilization of that anion. Now, what are we talking about here? Well, what we know is that when we've got opposite charges, they attract each other, right? When we've got like charges, they repel. So when we have opposite charges, they tend to stabilize. And then when we have like charges, they tend to destabilize. So in this instance, we've got the delta plus being closer to the O minus than it is in the second one, which means that we're going to have greater anion stability for A minus than B minus. Now, once we've got that, we can write a statement that links anion stability to acidity, and we can say that in this instance, A minus is more stable than B minus. That makes AH more acidic than BH. And the language there is important because we need to say, well, which anion's more stable? And then we need to relate that back to why the initial compounds, the ones we're actually talking about, these two up here, the ones with the F's on them that have the H's not removed yet, those are the ones that are acidic. The anions aren't acidic at all. So, I mean, sometimes I'll see answers like A minus is more acidic than B minus. It isn't. It's more stable, but it's not more acidic. Acidic means that it releases H+. These are the compounds that release the H+, not the anions. All right, does anybody have any questions? So the worst thing for students generally tends to be this business of having to write in the delta pluses and delta minuses. I don't know, a lot of students don't like doing it. I think it's against their religion or something. But they'll try to avoid writing them in. In fact, I'll get answers like A minus is more stable because F is closer. Well, it's kind of glossing over the reason. Really, there's a reason that it's more stable, and it's because the F being closer puts a delta plus closer to VO minus, which produces the stabilization. So it's not enough just to say, well, the F's closer, that makes it more stable. You have to include information about the delta pluses and delta minuses. If you're not doing that, you're not giving a complete answer. Anybody got any questions? Now, this one is somewhat similar. We are still dealing with a situation where the H plus gets removed and we end up with the negative charge on the O's in each instance. So the difference in stability, again, is not going to be explained by a difference in electronegativity on the atom where the negative charge resides. So that's not the issue here. The issue here has to do with the electronegativity of F in relation to Br. So again, I'll draw out the compounds as they appear here. Oops. So again, we can do the same thing as we did previously. We know we've got, it's basically CF versus CBr. Now, purposely here, I've drawn the CBr bond longer. And the reason for that is because Br is a much bigger atom than F is, which means that the bond will be longer. So this does have implications as to where the electrons are on average in relation to where the bromine or the fluorine are. And what we can say is that in the case of a CF bond, because the CF bond is shorter, the electrons are probably going to be closer to the F than they are to the bromine in the other example. And what that means is that we get a smaller delta minus on the Br than we do on the F. So let's put a big delta minus on the F and a little delta minus on the Br. And that means we have a big delta plus on the C versus a little delta plus on the C. So in this instance, the anion stability is going to be related to how big the delta plus charge is in each instance. So in the case of the one with the F, the delta plus is bigger, which produces a greater charge stabilization on the O negative. That makes the anion more stable. And since the A minus anion is more stable, it means the AH compound, the initial compound, is more acidic. Does anybody have any questions? Okay.
Yeah, I have one.
Yeah.
Which one would take priority? Like, let's say that the F was on the squiggly line to the left. Would bromine be a stronger acid? Could they be closer?
I wouldn't, that's the thing. I would never give you an example where I would mix those kinds of scenarios. I can only compare apples to apples. I don't know what would happen if I moved the F further away, whether the bromine would take precedence after that.
Okay.
And I wouldn't expect you to either. All right. Good question, though. Just realize I'll never give you an example or a scenario where that happens. Okay, one more scenario. This one is somewhat related. And this has to do with the sheer number of electronegative atoms we have attached to the anion. So in the case of this A minus over here, it's got two fluorines attached to the C versus the other one that only has one fluorine attached to the C. What I would want you to understand about that, what I would want you to understand about that is that if we have these two fluorines connected to the C, I'm just going to draw out the anions here, versus one fluorine connected to the C. We have delta minus on both of these Fs, which effectively means we've got double delta plus on that C versus one delta minus on the F in the second one and a delta plus on the C. So what happens is that the delta plus is double what it is when there's double what it is with two fluorines attached than what it is with one fluorine attached, which means that we're going to get much greater stabilization of the O negative when we have more fluorines or more electronegative atoms attached to the same atom. Does anybody have any questions? Okay, so let's do a summary here of the four different possible scenarios that we have here. And I'll show you a couple of worksheets, and then I'll show you how this relates to what we're seeing also in the test. Let's take it. Take all that out. Okay. So if scenario 1 is going to be a situation where we've got and X is more electronegative than Y, which would mean that that anion is more stable, which means the compound it came from is more acidic. So that's the first scenario. The second scenario is one of distance. And it's important to note that with the distance one, that the negative charge is on the same kind of atom. I've got X's there specifically, but look where the Y's are. They're just in different locations. So in this case, Y is closer to X minus. Oops, closer to X minus, which makes this one more stable. So in this case, Y is more electronegative than Z. Which would make this one again more stable, the first one with the Y on it. And the fourth one here I'll just add another Y for kicks up here. Okay, more Y, and that one would be the more stable anion. So I want you to notice that in the cases of 2, 3, and 4, the explanation is definitely going to involve delta pluses and delta minuses, whereas with the top one, where the negative charge is on completely different atoms, we don't use delta plus or delta minus to make any real headway with the explanation. So I'll just go ahead and put the delta pluses and delta minuses in here. So you can see that for scenario 1, we don't even use or talk about the delta pluses and delta minuses because they're not relevant in that situation. Does anybody have any questions about the 4 different scenarios that we're talking about here? Let's talk about some examples. And in the relative acid strength folder, I have a couple of worksheets that have complete answers on them. Let's talk about what these look like. I'm not going to go through all of them, just some of them, just to give you an idea of what we're looking at. Okay, let's have a look. Right. So these are the 4 scenarios that we're talking about. And I'll put them here, and I'm going to move this over a little bit. Sorry. There we go, that's better. So what I want you to be able to do is to be able to look at these and determine which scenario we're dealing with in figuring out which of these compounds is going to be more acidic. Now, the idea, of course, in all of these cases is that we're taking the H plus off first and looking at the anions. All right, look at number 1. What scenario is going to matter for number 1?
The O and the N.
Yeah, so it'll be number 1, right? Because the O is going to be negative and the N is going to be negative. So they're going to be completely different atoms. And we'll know that this OH here is going to be more acidic than the NH2 because the O negative is more stable than the N negative because O is more electronegative than N. So that's the first one. Now, I do have answers down here, but go into all of that. So just be aware of that. Take a look at number 3 here. Which scenario do you think is in play for number 3?
2.
Yeah, because of distance, right? The fluorine is in different locations. And what about number 4? What scenario is in play for number 4?
1.
Yeah, it is because this becomes C minus, that becomes O minus. And you'll notice they both have 3 Fs, so it's not scenario 4 because that would require different numbers of fluorines. All right, so those are relatively easy. Let me bring up ones that are a little bit more difficult. Again, these have answers attached to them as well. All right, look at number 2 there. What scenario are we dealing with for number 2?
I'm going to say 2 again.
Yep, yeah, because of the position of the fluorines relative to where the O negative is going to be. So the O negative, so the H plus will come off, that'll leave O negative in each of these cases here. Now, what about scenario 3? Sorry, number 3 here, I should say. Number 3,
I'm going
what
to say
scenario?
4.
Yeah, it's got to do with the number of fluorines we have. They're both located at the same point. This one has more fluorines at the same point than this one does. What about number 4? What scenario are we talking about there?
1.
No, I wouldn't say so. With number 4, they both become O negative, but we have a Br on this one and an F on this one, so it'd be scenario 3. All right, number 5. Okay, what scenario is going to be for number 5? This one's a little tricky. What scenario are we looking at for number 5? In each case, we lose H plus, it becomes CH2 minus.
3?
Yeah, it'd be 3 because we've got 3 Fs versus 3 Cls. And the F is more electronegative than the Cl. What about number 6? What scenario are we talking about there?
2.
That's 2 because of a distance. We've got 2 fluorines and 2 fluorines, but in this case, they're closer to the NH2 on the second one than they are on the first one. And number 7, that's also going to be 3 as well because we've got 2 Fs in the same location versus 2 Brs. All right, so that's how we do it. Let's take a look at the test questions, how they relate to what we just did. Oh, I've got it here. There we go. Oh, I do have a periodic table here. All right. Okay. I don't have to add it after all. Okay, so these are the kinds of questions. They're not that hard, actually. So out of these two, which compound is less acidic? All right, so if we call the top one A, the bottom one B, I guess you got a 50-50 shot. Which one's less acidic?
I'm going to say the bottom one.
Yeah, because the chlorine is further away. So if you took I'll just do the full work for that. I'll pull up another paint thing here. And we'll look at what the anions look like, because that's really the key to this, in my opinion. And you can see where the delta pluses are in each case in relation to where the O minus is, and that would lead you to be saying that the second one was more, or was less acidic. The first one was more acidic, because the anion is more stable. That's the reason that for the top one would be more acidic than the bottom one. Does anybody have any questions? Okay, question 5. Which compound has the less stable anion? So again, I'd be inclined to write out what the anions look like. That's really the key to all of this. And the anion is always going to be with one hydrogen removed from the more electronegative atom. So out of this one, which compound has the less stable anion? Well, again, it would be the top one, because N is less electronegative than O. Any questions? Okay. Now, the question 6 relates to the scenarios that we were just talking about. And for this one, it says, the reason that one of these anions of these compounds is more stable than the other. And people hate these questions because they're word questions. You have to really read them closely to make sure you understand exactly what you're doing. And it's got to do, in this case, with scenario 1, because we're going to have C minus versus N minus. So I have to figure out which answer relates to that. Now, the closer here, we know that that's got to do with scenario 2. The greater number of electronegative atoms, that's got to do with scenario 4. The negative charge is on a different atom, and one of those more atoms is more electronegative than the other element. That's got to do with scenario 1, so that would be the answer. An atom attached to the anion is more electronegative than an atom attached to another anion. So that would be more to do with scenario 2. In scenario 3 in that case. So in this, so the answer to this one would be the third answer. Any questions? Okay. What's the correct statement that links the acidity of the anions to stability? Yeah, okay. So we got compound A, and we talk about the anions as well. So the reason here is because the anion of B is going to be more stable than the anion of A. So that's going to be the reason that B will be more acidic than A. So we need to find something where compound, it says here, so something about the anion. So anion of B is more stable than the anion of A. No, that's not it. So anion of B is more acidic than the anion of A. No, that's not it. Anion of B is more stable than the anion of A, so compound B is more acidic than compound A. So that would be the correct example. That would be the correct wording there. So again, people don't like this either because there's so many words here and it's so misleading. But again, it's all about understanding that it's the stability of the anions that gives us an idea about which of these two compounds is more acidic than the other. Does anybody have any questions about number 7? Okay. So I would recommend going through those worksheets in the relative acidity folder. Sorry, relative acid strength folder. I go through these. I'd also do the fun quiz as well, which really has similar problems to what's on the test. And then I would also definitely go through the test questions and definitely understand what you need to be looking for in those questions as well. All right. Does anybody have any other questions about the relative acid strength portion of things? Okay, just want to see how far I have to get today. Okay, Ka calculations involved. All right. Okay. All right. These next slides, I'm going to kind of skip through them a bit. They got some interesting information, but it's not really germane to what we're talking about. It's more to sort of help you out a bit here. So what we know is that if we've got carbon, nitrogen, oxygen, and fluorine, that we know there's certain kinds of bonds they're going to have if they're neutral. We know that fluorine will bond, will have usually one bond, oxygen will have two, nitrogen will have three, and carbon will have four. Now the thing is, when these things have fewer bonds than they're supposed to have, like with oxygen, when oxygen has one bond, it's generally negative, and when oxygen has three bonds, it's generally positive. Likewise with nitrogen, when it has two bonds, it's negative. When it has four bonds, it's positive. Now, carbon is a bit of a weird one because it's in the middle. It could go either way. It could be positive or negative, depending upon if it has an extra electron or if it's lost an electron. So that one can be a bit weird. But the rest of it, my point is that generally when things have fewer bonds than they're supposed to have, they tend to have a negative charge, and then when they have more bonds, they tend to have a positive charge. And by way of example, I can look at something like this. So in this instance, you see you've got an OH and an OH, and the O here has two bonds and it has no charge on it. And then when we take the H plus off, the O only has one bond, so it gets a negative charge. That's really all I'm trying to say. Does anybody have any questions about that? So I've got some examples here of those kinds of scenarios. I'm going to skip over the resonance structures, but if you this will be more helpful if you're going to do the fun quiz. So I'm going to leave that to you to look at, because there may be instances in the fun quiz to do with acidity that might relate to resonance. So I'm going to leave that to you. I'm not actually going to cover resonance for this test anyway. All right, let's look at determining the Ka given the pH. All right, let's talk about what pH is first. So pH is the negative log of the hydrogen ion concentration. And as a general rule, if you want to find the pH of something, and generally speaking, if we're looking at pH, it's usually something like this. The concentration of H plus is generally X times 10 to the negative Y, something that's fairly small. And if you want to find out the pH in general, the pH will be approximately what the exponent is with the negative removed. Yeah, if you don't believe me, you can always try this out. Why did that disappear? I don't like that at all. So the pH is the negative log of the hydrogen ion concentration. So let's let me do an example here. Let's say your concentration of H plus is 6.5 times 10 to the negative 6 molar. I can tell you the pH is approximately going to be 6. Now, if you wanted to do this in your calculator, the way you do it is you would put, I'd like you to try this, please. Put 6.5 times 10 to the negative 6 into your calculator and then hit the log button. Or, yeah, depending on what kind of calculator you got, you might put log and then that number. If it's a graphing calculator, you'll do that. And hopefully, what has anybody done it? Let's see how many people we've got here. 6. Okay. What's your exact answer to that?
5.19.
Okay, yeah, I'd say it's close, but it's not going to be exact, of course, but it's going to be close. So 5.19 is what you get there. And that's the negative log, right? Because the log actually comes out to be negative 5.19, but we take the negative of that, and that gives us the pH. So there is no negative log button, of course, on your calculator. You have to do the log first and then take the negative of that value. Does anybody have any questions? So that would be the pH for that one. Now, the little p, excuse me, the little p out in front means take the negative log. That's all it means. So pH, take the negative log of H plus. POH, take the negative log of OH minus. pKa, take the negative log of the Ka. pKb, take the negative log of the Kb. P grandmother, take the negative log of your grandmother. It doesn't matter, but the little p just tells you that you're going to take the negative log of something. So there's this thing we can talk about with regard to water, and I'm just going to go through a little bit of that. What we know about water is that it actually dissociates, at least to a very small degree, into H plus and OH minus by a 1-to-1 ratio. Not much H plus and OH minus, but it does do that. So we can write a K expression for that, that looks like this. H plus times OH minus over the concentration of water. Now, it turns out the concentration of water isn't going to change much. We could work out the concentration of water. It's going to be moles of H2O per liter of H2O. And we know that we can figure out the moles of H2O. It's going to be about, well, the moles of H2O, we're talking about 1 liter of H2O is about 1,000 grams of H2O, which is about 55.5 moles of H2O. Now, how do I get that? Well, I know 1 liter is about 1,000 mils. The density of water is about 1 gram per mil. And then in order to get the moles, I can take the 1,000 divided by the molecular weight of water. So 1,000 divided by 18 be about 55.5 or something like that. So the concentration of water here is about 55.5 moles per liter. And that is not going to change much. I mean, that's really concentrated. That's really constant. It's effectively constant. So what we can do is we can take this H2O and tie it in with the K, and we end up with this new constant we're calling Kw, which is equal to the OH minus times the H plus. And Kw actually has a set value as being 10 to the negative 14. So we can actually, in a regular solution of water then, if we know what Kw is, then we know what H plus and OH minus are. If Kw is 10 to the negative 14, then H plus would have to be 10 to the negative 7, and OH minus would have to be 10 to the negative 7. And the pH then would be 7. The pOH would be 7. And what's the relevance of the pH being 7? Anybody? Got any ideas about the pH being 7, what that means?
Neutral.
Neutral. And that's where that comes from. That's where the pH of 7 being neutral on the scale comes from. It comes from the fact that water dissociates, has that Kw of 10 to the negative 14, which means that we've got 10 to the negative 7 times 10 to the negative 7, which would be 10 to the negative 14, which means the pH is 7. The pOH is 7 as well. Further, it means that if we take the logs of everything here, we get this relationship where pH plus POH is equal to 14. So that's important as well. pH plus POH equals 14. And 14, of course, is the basis of the pH scale. It's the top range, right? Does anybody have any questions? So that's the origin of the pH scale right there. The fact that it's 14 is the top, and that 7 is neutral, and that pH plus POH is equal to 14. All right, does anybody have any questions? So we can apply all this now to the dissociation constants for acids and bases. And I've got that down here. If you've got Ka, the little a here stands for, does anybody know what the A stands for? Just as a guess. Anybody want to guess what the A stands for?
I really can't think of anything.
Anybody got any ideas? Anybody want to take a stab what the A stands for?
Acid.
Acid, yes. The A stands for acid. Any idea what the B stands for?
Base.
Base, yeah, that's right. So if it's A for acid, that means we're producing H+, and if it's B for base, it means we're producing OH-. So we can write equations for the acidity constant for this Ka. It's always going to have H+ and A-. So the Ka is going to be H+ times A- over HA. And for Kb, since we're forming OH-, we get A+ plus OH-. And that's over AH. That'll give us the Kb value. All right, so that's going to be the basis of what we're going to be talking about from here. And it's probably going to be easier for me to do some examples at this point. All right, so here is the kind of problem that we'll be starting out with. We're told that the pH of a solution, 0.2 molar solution, 0.20 molar solution of HF is 1.92. Determine the pKa for HF. So let's see how we manage that. This problem is actually related to something we've already seen, and that was question 4 of test 1, where we were figuring out the equilibrium constants. And you'll remember we were doing something similar to here, to what we did there, where we were using these Z values. But with this, it's actually a little easier to explain. So let's go through the process here and decide exactly what we're doing here. So let's look at what we've got in the question. We've got HF in the question, and we're looking for pKa. So I know that the first thing I'm going to have to do is split this up into H+ and something, because we want pKa. And the A here is for acid, which means that we know we need H+. And if it's H+, then it's going to be F- that we're getting with it. Does anybody have any questions so far about what I'm doing? So again, the key is what we're looking for, pKa, which is about acid. So I know that H+ is going to be what I'm going to be looking for. Any questions? So initially, from the problem, I can see that the molarity of HF is going to be 0.20. The H+ is going to be 0, the F- is going to be 0. Because initially all we have is just the HFs in the solution. Now at equilibrium, the HF is going to break apart and we're going to get ZH+ and ZF-. So I'll just show you very simply how that works. So let's say you've got 3 HFs, or 4 HFs. This is initially. Then after a time, and I'm just making this up, at equilibrium, then 2 of those might split apart. And if that happens, we end up with 2 H pluses and 2 F minuses. So each HF will split up into H plus and F minus. Now, my point is here that the HF has gone down in concentration by the number of HFs that have broken apart, which I think makes a lot of sense. And by the number of HFs that have broken apart, we've gotten 1 H plus and 1 F minus for each one that breaks apart. So that's why it makes sense that it's 0.20 minus Z, and we get Z and Z for the H plus and the F minus. Don't overthink it, folks. It's not really that difficult. Does anybody have any questions? Now, in order to get the Ka value, we do have an equilibrium constant expression that we can come up with for this. And that is that Ka, whoops. Well, what happened? That's weird. Oh, it used cropped, I guess. That's unfortunate. Okay. I'm just going to delete that completely. That went nuts. Okay. So the Ka is going to be H plus times F minus over HF. Now that's all at equilibrium, of course, all those values. So you can see that's how we're getting the Z squared over 0.20 minus Z. Does anybody have any questions about that? Now we need a way to find Z, and we've already got that because we've got the pH of the solution. The pH can be converted into the hydrogen ion concentration. So we know that pH is the negative log of the hydrogen ion concentration. In order to solve for the hydrogen ion concentration, H plus, it's going to be 10 to the negative pH. Now, how do I get that? Well, I'll show you. So what we can do is, if we've got pH equals negative log of H plus, then we know that negative pH is equal to the log of H plus. Now look on your calculator. Look on your calculator. What do you see as the second function for the log button? Take a look. I'm waiting. What do you see as the second function on the log button of your calculator?
Are you referring to 10 to the exponent of x?
10 to the x, right? That's what it says. So that's the opposite, or the inverse log, if you will. 10 to the negative pH equals H plus. That's where that comes from. Does anybody have any questions? So what that means is that if we're looking for we got the pH, and that pH is actually at equilibrium. It's 1.92. So pH is, whoops, did that again. So pH is going to be 1.92, which means the concentration of H plus is going to be 10 to the negative 1.92. So there's a couple of ways you can put that into your calculator. You can do negative 1.92 and then do second function log. That'll do the trick. And then that comes out to be 0.0120. Molar. Anybody got any questions? So that's Z. That's what Z looks like. So that is the hydrogen ion concentration at equilibrium, which is actually Z. Does anybody have any questions so far? Once we've got Z, we can solve for Ka, and then we can figure out what pKa is. But let's do Ka first. And we'll pay also here special attention to the significant figures as we do this work. So it's going to be Z squared over 0.20 minus Z. If I do the plugging in here, 0.0120 squared over 0.20 minus 0.0120. Now we're mixing operations here, so this is going to go by the number of places past the decimal. So that comes out to be 0.0120 squared over 0.19. And then that comes out to be two significant figures, 7.6 times 10 to the negative 4. So that would be the Ka value. Does anybody have any questions about that? The most common mistake that people make is that they don't do that subtraction there first. But because that's subtraction, the other things are multiplication and division, we have to get the significant figures from the subtraction first. That's why that step is so important. The last step, getting the pKa, if we know that the Ka is 7.6 times 10 to the negative 4, the pKa is going to be the negative log of the Ka. So how would you do that? Well, you'd put that into your calculator. You take the log, and then you take the negative of that number. So go ahead and try that, and make sure you're getting a pKa of 3.12. I'll explain how to get that significant figures from the log in a second, but just make sure you're getting close to that answer. All right, does anybody have any problems with getting the pKa value?
Yeah, I am.
Okay, so
I'm implementing the negative log, and then I'm putting Ka into it. I'm getting what?
So you should take the log first and then take the negative of that value. So take the log of 7.6 times 10 to the negative 4 by itself, and then take the negative of that value. So do the log first and then take the negative of that value, Jack.
All right.
You should get close to 3.12, right?
Yeah.
All right.
Yeah, I got it.
Okay.
Simple mistake.
So the Ka then has two significant figures. To get the log, the number of places past the decimal will always match the number of significant figures you had initially. So we have two sig figs, which means two decimal places in the log. Now the reason for this has to do with, well, I'll do a little bit of log magic here. If you take a log of A times 10 to the negative B, that is going to be the same as log of A plus log, well, it's going to be effectively negative B. Because when you take the log of 10 to the power of something, then it just becomes that number. So you just end up again with the exponent. The thing here, though, is that B is a counting number. And the A here is the one that's subject to significant figures. So the B here always ends up out the front. So we're not really interested in the significant figures of what's out the front because that relates to the exponent, which was a counting number. So the only thing that really matters for the significant figures will be the log of A, which will be whatever's past the decimal. So I hope that makes sense. That's the reasoning behind it. Does anybody have any questions? No, you're all fine with that. I don't believe that, but anyway. All right. Okay, let's look at how we might handle a base problem. So we're looking here for KB, and that's the key there is the B. Little b there means base. So what I have to do is come up with a way to get an OH minus out of that. Now, we can't get OH minus just by taking CH3 and H2 and trying to pull OH minus from it. The definition of a base is that when you put it in water, it forms OH minus. Now, sometimes these things have OH minus in them, and that's how we get the OH minus, and that's easy. Sometimes, though, it's not that easy. We need to get the OH minus from adding water. Thus, when we're trying to get OH minus, we're always going to need to have water as one of the reactants because that's always going to be the source of our OH minus when we have the base. So in general, it's always going to look like this. So water plus B will produce B, H plus, and OH minus. And if you remember what we were talking about previously, about the base, that if we want to get the conjugate acid, we would add H plus to it. And if we want to get the conjugate base, we take H plus away. Effectively, we're adding H plus to the B, and we're taking H plus away from the water. And that's what we're getting here. So water is effectively the B is the base. Water is effectively the acid here. This is going to be the conjugate acid for the BH plus, and the OH minus is going to be the conjugate base. But the whole point here is that the water splits apart effectively into H plus and OH minus. The H plus goes with the B, and the OH minus goes by itself. We know we're getting the OH minus because it says Kb, and that's what bases do. They form OH minus in solution. And again, students to test these kinds of problems because they're never really sure about how to break the solution up so we get everything the right charges on it. But let's have a look at what this one's going on. What's going on with this one here? So we've got H2O plus CH3 and H2. So we know we're getting OH minus, and the rest of it is going to be CH3 and H3 with a plus charge on it. Whoops, it's OH minus. Sorry. There we go. Now the reason I know it's OH minus again is because of the base, it's Kb. The H plus is from the water and it gets added to the CH3 and H2, so that becomes CH3 and H3 with a plus on it because we've added H plus to it. Does anybody have any questions? Okay. So the initial, and then we've got the equilibrium as well. So for CH3 and H2 is going to be 0.30 and 0 initially on the products. And then at equilibrium be 0.30 minus Z and Z on the products. So same logic as before. Now you'll notice in this instance, we need the OH minus concentration. And what we're given, though, is a pH. So we're going to actually have to solve for a pOH first and then get the concentration of OH minus from there. So the relationship that we're using is this one, and that is that pH plus pOH is equal to 14, which means we can solve for the OH minus. So the pOH, or the pOH, is going to be 14 minus the pH, which is 14 minus 9.97. And so that allows us to get, move this over here. That allows us to get 4.03 as the pOH, and then to get the concentration of OH minus, is going to be 10 to the negative pOH, which would be 10 to the negative 4.03. Which would be 9.33 times 10 to the negative 5. Which happens to be our Z value. So we have to go a little bit further than we did previously because we were given the pH here instead of the pOH. And it's the pOH that's going to lead me to be able to get the OH minus here in the problem. Now, after we've done that, we can solve for the Kb. Because Kb now is going to be, sorry. Kb is going to be the OH minus times the CH3NH3 plus over the CH3NH2 we've got the Z squared over 0.30 minus Z down here. We can sub in the Z's. We'll get 9.33 times 10 to the negative 5 squared over 0.30 minus 9.33 times 10 to the negative 5. Now, effectively, if we look at that, that's going to be 0.30 minus 0.00000933. And if we look at significant figures, then that is going to come out to be 0.30. So it's two places past the decimal versus, what, 7 places past the decimal. So the answer comes out to 2 places past the decimal. You put that in your calculator, that's what you'll get is 0.30. So that allows us to get 2.9 times 10 to the negative 8, and then we get the pKb by taking the negative log of that. And again, two significant figures, 2 decimal places. Now, I know I went through that fairly quickly for the last part. I'm going to continue with this on Tuesday, and I'm going to show you what the problems look like on the test. All right, so we'll continue with this on Tuesday.
Okay. I can go do a cheat.
Sorry, Jack. You all right? Sorry.
That was not me that said that.
Oh, okay.
I was going to say thank you.
Oh, okay. Fair enough. Thank you. All right. I'll see you all later. If anybody wants to hang around and ask me anything, they can.
Thank you. Bye.
Bye.